Hey everybody, it's Mr. Sonnenberg again. This is installment number 2 of Ionic bonding. This is Tuesday's homework specifically. Yesterday's video I think is pretty important and should be watched first if you're still having some struggles with the basics to ionic bonding, understanding electron configurations, Bohr models, etc. The oxidation numbers in particular are covered in the first video, so by all means you can review that one. I'll try to make this one a little shorter, but it will cover tonight's homework. So it is over bonding basics, whereas yesterday was the atomic structure practice. But again, I would encourage you to watch the first one prior to this one. At any point, you can pause, rewind, fast forward. These videos are designed to help people who want a little extra help, or if you've missed some time, missed some instruction, and you need the basics so that you understand what's going on either way. But the first thing I'd like you to do is make sure for today you just need a pencil and your own periodic table. And so go ahead and pause me and go get those things. Now, the reason I asked you to get your own periodic table is because I definitely want to make sure that you can have a periodic table that you can write on. I'm going to go ahead and ask you, if you haven't already done this, a lot of people did it in class already, I want to go ahead and ask you to label the top of your periodic table for group 1 and group 2. And these are going to represent the number of valence electrons. So what's consistent about the groups I'm going to show you is why, remember, families or groups all share similar properties. And one of the patterns of the periodic table is to focus on group 1 and 2. They each have 1 valence and 2 valence electrons respectively. Skip the transition metals for now. They all have things in common in their own right, but their valence electrons jump around a little bit. But we're going to jump to group 13. Group 13, the boron family, have 3 valence electrons. Group 14, the carbon family, have 4 valence electrons. Group 15, the nitrogen family, have 5 valence electrons. Group 16, the oxygen family, have 6 valence electrons. You can see the pattern here. The halogen gases, which are group 17, have 7. And group 18, the noble gases, with the exception of helium, all have 8 valence electrons. Helium has but 2, but it has a full shell, which is what all of these elements have in common. They are completely inert and do not react with any other elements at all. And so they are the so-called noble gases. For tonight's homework, the first part of it, was to work on this chart, and a periodic table with the top groups labeled is really all you need for this. And if you look and find each of these elements where they belong, it's pretty easy to fill out. If you find sodium, it's element number 11, which means it's got 11 protons and in turn 11 electrons. It's part of group 1, so it's got 1 valence electron. Its oxidation number, therefore, is 1+. It's a so-called cation. And the reason for that is because it's got 1 valence electron. It's much easier for it to lose 1, leaving the atom more positively charged during ionization, than it is to gain 1, which would make it more negative. Chlorine is an anion. It's got 17, and 7 valence electrons, and its outer shell has 7, which means it's easier for it to gain 1, to gain the full shell during ionization, and it would make that atom more negatively charged during that chemical reaction. Beryllium is element number 4, if you find that on the periodic table. Beryllium has, therefore, 4 electrons and 4 protons, and it's got 2 valence electrons, and beryllium, therefore, has an oxidation number of +2. If you are still a little unclear on these, I would invite you to go back to the first video to make sure you're clear on oxidation numbers. Let's move on to the first problem that we did in class, which was potassium and fluorine. Potassium is an alkali metal, and all alkali metals are group 1 metals, so therefore they have 1 valence electron. And because they have 1 valence electron, they love to react. It's very easy for them. They're very reactive. All they have to do is give up 1 electron to involve themselves in a chemical reaction. And this particular one is going to chemically react with fluorine or form an ionic bond with fluorine. And fluorine is a halogen. Fluorine is a member of a family that has 7 valence electrons. And it, in its own right, has a real easy time reacting with certain elements like the alkali metals. You can see it's a bit of a puzzle piece. It fits very nicely right here. Potassium to fluorine forms the chemical bond, the ionic bond of potassium fluoride. And part 2 of this particular homework assignment is to draw the oxidation numbers, then draw the final formula, which is Kf, or potassium fluoride. Let's move on to the second one. The second one's a little tougher, but this one will probably make things a little bit more clear. Magnesium is an alkaline earth metal. If you look on the periodic table, it is element number 12 in group 2. All group 2 elements have 2 valence electrons. So for today, I'm going to write them on the right-hand side to make them a little easier to deal with. We have iodine, which is also a halogen. And because it's a halogen, it also has 7 valence electrons. Now, we know from the first problem that we can place 1 electron over to the iodine and fill its shell. But what do we do with this one? Well, the answer, some of you knew it in class today, is to find another iodine. After all, there are trillions and trillions of atoms that might be in a given place for all of these atoms to combine. And the idea is it's just a specific ratio. For every magnesium atom, 2 iodines can combine with it to form a compound called magnesium iodide. We write the we write the oxidation numbers, Mg2+, I1-, but because there are 2 iodines, we write a subscript below. The final formula is MgI2, magnesium iodide. This step simply shows that you understand the ionization part. And then we'll do one more. Sodium and oxygen. Sodium is an alkali metal, as you probably recall. It's got 1 valence electron. Oxygen is a member of group 16. If you look, let's go back to our periodic. Do you know what we should do? Let's go back to our periodic table here. Group 16 has 6 valence electrons. So we can go 1, 2, 3, 4, 5, 6. Now, this one's a little different than the previous one, where we had an alkaline earth metal mixing with a halogen. Now we have oxygen mixing with sodium, an alkali metal. Well, we know we can fit 1 there, but we have this empty spot here. How are we going to fill that empty spot so that a compound with an equal number of protons and electrons can be formed? Well, we add another sodium. So it becomes 2 sodiums for every oxygen atom, and now we have Na, 1+ with a subscript of 2. I am going to rewrite that because it is very messy. My writing with this smartboard is not very good. 1+, and there are 2 of them. That is what that 2 means right here. There are 2 sodium atoms for this oxygen, which is got an oxidation number of 2-. So the final formula is Na2O. Na2O. There you go. Sodium oxide, not to be mistaken with sodium hydroxide, which adds a little hydrogen in there and was formed when we put sodium in water. This is a little bit of a different compound. It's also a white solid, in its natural form. But in any event, that is today's lesson and covers everything we talked about in class. Tomorrow there will be another video, but that will be strictly for the honors, and it will cover covalent bonding. Again, rewatch this as many times as necessary, and if you ever have any questions, you come and talk to me. So